Hello APC Mechanics students, today we'll solve the past paper FRQ 2019 set 1, exercise number 2. Then always remember that the figure happens to be above the exercise itself. A pendulum of length capital L consists of block 1 of mass 3m attached to the end of a string. Block 1 is released from rest. This is important, which means the initial kinetic energy at this point is 0. With the string horizontal as shown above, at the bottom of its swing, block 1 collides with block 2 of mass capital M. So notice that the masses are given in terms of each other in order to apply later on the cancellation effect, which is also initially at rest. At the edge of a table of a height 2L, block 1 never touches the table. As a result of the collision, block 2 is launched horizontally from the table, landing on the floor a distance 4L from the base of the table. Then as block 1 is released at this position, and notice carefully block 1 at this position, it won't be in contact with the table. Collision will happen between block 1 and block 2, giving momentum to block 2, and block 2 will be launched horizontally from the table. After the collision, block 1 continues forward and swings up. Now what's happening to block 1 after the collision? Block 2 will be launched horizontally, while block 1 will continue its swing. At its highest point means the final kinetic energy of the block 1 would be 0. The string makes an angle theta max to the vertical. Air resistance and friction are negligible, which means we can apply the conservation of energy, express all algebraic answers in terms of ml and physical constants as appropriate. So for all the parts, whenever we determine something, we need to make sure it's being expressed in terms of m and l. Perfect. In part A, they're asking us to determine the speed of block 1 at the bottom of its swing just before it makes contact with the block 2. Now we need to determine the speed of the block 1 at this point and before being in contact with 2, and this is done using conservation of energy. But before doing so, we need to specify our PE level. Therefore, let me say take the PE level to be the horizontal passing through the table. Now we can directly guess what would be the expression of the speed under the influence of gravity. It would be given by the radical of 2gl, which is a coefficient, multiplied by gl. This is the only way to construct speed under the influence of gravity. And for this reason, because we're applying a big law, let me say apply the conservation of energy. Which means energy initial would be equal to energy final, and energy is about being kinetic and gravitational potential energy. Now the block 1 being released from rest, so that would be 0, and based on our choice, the final gravitational potential energy would be 0. Now remember that the mass of the block 1 is given by 3m, so that would be 3m multiplied by g multiplied by h is equal to half 3m multiplied by the final velocity that we wish to determine, then v square. Here we can apply the cancellation effect for the masses. Now what is the h? Because the string is initially horizontal and becomes completely vertical, then the height from this point to this point, or that would be our PE level, and the height from the initial position to the PE level, that would be equal to h, which is the length of the string. Then we would have g multiplied by l is equal to half v square. Then in this case, v square is equal to the double of gl. Then indeed, the speed of block 1 momentarily before the impact is given by the square root of 2gl. Now in part B on the dot below, which represents a block 1, draw and label the forces, not components, that act on block 1 just before it makes contact with block 2. Now just before making contact with a block 2, that would be the position of block 1. Now what are the forces acting on block 1? That would be the pull of gravity down. and we have the tension in the string up. And notice that block 1 is not being in contact with the table, so there is the normal push. Now, however, if you notice carefully, they're telling us forces with a greater magnitude should be represented by longer vectors. And since block 1 is performing circular motion, and that would be the center of the circular motion, now pull of gravity is, the tension is pointing toward the center and the pull of gravity is away. Therefore, the tension in magnitude should be greater than the pull of gravity, and this should be apparent from our FBD. Then let me do the pull of gravity to be 2 grids downward. And let me represent the tension force to be greater in magnitude, represented by 3 grids. And now in part C, they're asking us to derive an expression of the force. So whenever they mention a force, we should directly think of Newton. In the string, when the string is vertical just before block 1, makes contact with block 2. If you need to draw anything other than what you have shown in part B to assist in your solution, use the space below. Do not add anything to the figure in part B. And this is usually done whenever we have an FBD, so we don't add anything to our FBD. And because we need to determine the tension, so here also let me mention again that the speed that we have derived in part A only depends on M and L. So this is done by applying Newton's second law. Why also we should think of Newton's second law? Because the previous part is about an FBD. So let me say apply Newton's second law. Then always whenever we're applying a big law, we need to mention the law that we're using. Now F naught is given by MA. Now remember that we're interested in determining the tension at the same instant that we have represented the FBD. Therefore, the forces that are acting on the block 1 are given by the pull of gravity, and the tension equals to MA. Now remember, this is a vector equation here. Let me say that the mass is given by 3m multiplied by A, which is the mass of block 1. Now this is a vector equation. It gives the birth to several linear equations. We need to specify our direction along we're projecting, and this happens to be the centripetal direction along the circular motion. Then let me say projection along the centripetal direction. Now we need to understand in this case what is the positive direction and what is the negative direction. Always forces pointing toward the center would be positive and pointing away would be negative. The tension force pointing toward the center, so that would be positive. And the pull of gravity is pointing away from the center, that would be negative. And remember that here we're projecting the acceleration along the centripetal direction, so that would be 3m AC. Now the pull of gravity is given by minus 3mg plus the tension force, and in this case the centripetal acceleration, as we know, is given by v square divided by the radius of the circle, which is basically the length of the string, and that would be L. Now remember that our answers should be expressed in terms of M and L, so the thing is that we're interested in determining the tension force. So the only thing that we want to do is replace V with M and L, and indeed in part A we have determined at this specific instant that V is given by radical 2GL. Then here let me continue my equation and say minus 3mg plus the tension force is equal to 3m divided by L multiplied by the square root of 2GL to the power of 2. Now this would cancel, so we would have 2GL. Now this would cancel. Here we have 6gm, so the tension force is basically given by 3mg plus 6mg. Then in this case, indeed, the tension force in terms of the given quantities is given by 9mg. Now they're telling us for parts D to G, basically parts D, F, and G, the value for the length of the pendulum L is 75 centimeters. So they have put forward a numerical value for the length. Then we wish to calculate all the following quantities. as in numerics. And indeed, in part they're telling us calculate, they didn't tell us derive or express. So we need to have a numerical value of the time between the instant block 2 leaves the table and the instant it first contacts the floor. Now, although we don't know the launching speed of the block 2, however, the time taken for block 2 from the table to the ground doesn't depend on the initial velocity, because we can utilize the motion along the vertical. Then in this case, if we choose our origin to be here and the positive direction to be up, then the acceleration along the vertical would be minus g. The launching angle is 0, which means cosine theta is 0, and sine theta would be, cosine theta is equal to 1 and sine theta is equal to 0. And the final vertical position would be minus 2L, because we're measuring in the negative direction. So here let me say, and I can directly give you the expression of the time, because this is basically along the vertical free fall. It's given by the square root of 2h divided by g, and the height that we're going down is given by 2L, so that would be basically 4L divided by g. But we need to show our work. Then the equation for the vertical position is given by y is equal to y0 plus v0 sine theta t minus half gt square. Now based on our choice, that would be 0, that would be minus 2L, and that would be 0. Then minus 2L equals minus half gt square. Now negative with negative would cancel, t square would be 4L divided by g. Then t would be given by the square root of 4L divided by g, which is the square root of 4. Now this is centimeters, and in order to convert from centimeters to meters, we divide by 100. Then plugging this expression on the calculator, we're gonna find the time needed for the block to reach the ground is given by 0.55 seconds. Now in part E, calculate the speed of block 2 as it leaves the table. Now we know that the variables of motion, the vertical and the horizontal for block 2, are independent. The only dependent variable, or the variable that unifies both, is the time. And we know that the initial launch here is horizontal, and the equation is given by x is equal to x0 plus v0 cosine theta t. Now we know the value of t, which is unified for vertical and horizontal, and we know that x in this case would be the horizontal distance, which is 4L. This is our origin here. Then we can determine the initial speed of the block. Then in this case I would say that x is equal to x0 plus v0 cosine theta t. Let me say that this is cosine theta t. Now that would be 1, that would be 0, that would be 4L, and v0 in this case I'm gonna name it to be v2. Then 4L is given by v2 multiplied by t, and we have the value of t, which is given by 0.55 seconds. Then v2 would be given by 4L divided by t, which is 4 multiplied by 0.75 divided by the time lapse, which is 0.55. Then plugging that expression on the calculator, we would find that the initial velocity of the block 2 after the collision is given by 5.45 meter per second. Now what's happening here, basically, before I proceed, if the aim of the exercise is to determine theta max, then we need, without saying so. Yes, if our aim is to determine theta max, so we need to determine the speed of the block just after the collision. This is the only quantity that we haven't determined yet. Now before the collision we know the speed of the block 1, and after collision now we know the speed of the block 2. So using the conservation of momentum, for example, we can determine the speed of the block 1 immediately after collision. And indeed, if we check, they're telling us calculate the speed of block 1 just after it collides with the block 2. Notice that the mass of the block 1 is 3m and the mass of the block is m, so we can apply the cancellation effect without knowing the value of m, and they don't stick to each other. So here in this case, because they have mentioned a keyword in the exercise which is collides, which means we're gonna apply the conservation of linear momentum, then apply conservation of linear momentum, which means initial linear momentum would be equal to final linear momentum. Now initially, before the collision happens, the only between the blocks 1 and 2 that have momentum is block 1, and it's given by its mass, which is 3m, multiplied by the speed that we have determined in part A, which is given by radical 2gl. So I would name it to bv. Now we're interested in determining the final linear momentum of the system that consists of the motion of the block 1 and the block 2. So block 1 of mass 3m, and both of them, they are pointing in the positive direction, multiplied by v1 final that we want to determine, plus the mass of the block 2 multiplied by the speed v2 that we have determined in this part. And remember that all of these are vector quantities, v1f and v2. Now we can apply the cancellation effect for the masses. Now 3, that would be the radical of 2gl, which we have determined in part A, which is equal to 3v1f that we wish to determine, plus the speed of the block 2, which is given by 5.45. Now I will isolate v1f, then v1f in this case would be what? Now this would be taken to the left hand side, and we would divide by 3, so that would be 3 radical 2gl minus v2 divided by 3. Then that would be 3 radical 2, now g is given by 9.81, and the value of L is given by 0.75, minus the value of v2, which is 5.45, and dividing by the value, which is 3. Plugging this expression on the calculator, we would find that the final velocity of the block 1 immediately after the collision is given by 2.02 meters per second. Now how this again is correlated to the value of the maximum angle. Now as block 2 is launched from the table, block 1 will continue its swing up. Now this is theta maximum, and it's the angle with respect to the vertical. And the moment they mention this is a vertical position, then the final kinetic energy here would be 0. And remember that our P level, it's still set here. Then initially at this point, the block 1 has 0 gravitational potential energy, however it has kinetic energy. And at this point, it's completely converted to gravitational potential energy, and the final kinetic energy would be 0. Now gravitational potential energy, it's about position, which is given by mgh. How h would be related to the angle? Remember that this is a pendulum, and the angle is given with the vertical. In this case, h is given by the length of the string multiplied by 1 minus cosine theta, and we can solve for cosine theta. Then indeed in part G, they're asking us to calculate the angle theta max that the strings makes with the vertical as shown in the original figure when block 1 is at its highest point after the collision. Highest point, this is very important, which means the final kinetic energy would be 0. Now our P level, it's already set through the table. So now let's again just mention apply conservation of energy. And remember here we need to determine numerical value for theta, because that is required from us from parts D to G, since L now is set to 75 centimeters. Then energy initial in this case is equal to energy final. What does the initial point represent? It's the point immediately after the collision when the block it's still on the table, almost but not in contact. This is about being a kinetic energy initial plus a gravitational potential energy initial, which is equal to kinetic energy final plus a gravitational potential energy final. So the maximum position, then this is 0. Through the P level, this is 0. The initial kinetic energy is given by half the mass of block 1. Again, it's 3m. And here we should pay attention which speed, since we're talking about after collision, then that would be v square 1 final, since we have both speeds for block 1. And this is 0, the final gravitational potential energy, that would be 3 mgh, and between brackets we can write that h is related to the angle with the vertical by given L into 1 minus cosine theta. Now we can apply the cancellation effect for the masses, and then have v square 1f is equal to g into L into 1 minus cosine theta. Then we need to search for cosine theta, then invert this function. Now gl is on the top, then it becomes at the bottom, then v square 1f divided by 2gl is given by 1 minus cosine theta. And basically first we're searching for cosine theta, then how to solve for this equation. This is a linear equation we isolated. Then why this is a linear equation? This depends on how your promotion is going. If I'm promoting cosine theta to be x, then this is a linear equation. If I'm promoting theta to be variable, this is trigonometric equation. Then cosine theta would be given by 1 minus v square 1f divided by 2gl. And the final speed for block 1 after collision is given by 2.02 to the power of 2 divided by 2, 9.81, multiplied by the length of the string, which is 0.75. Now in this case cosine theta is given by 0.72, and it's more reasonable, so let me say that this is theta max. It's more reasonable in such type of exercises to determine our angle in degrees, so that would be the inverse function of the value 0.72, the cosine function, and the angle it's almost given by 43.9 degrees. Then the maximum opening angle of the block 1 after the collision with respect to the vertical is given by 43.9 degrees. And that's it for me in this video, guys. See you soon in a new one.